everybody, it's Mrs. Hofferberth. Let's talk about electrolysis today. In electrolysis, electrical energy is used to cause a non-thermodynamically favorable redox process to occur. So for example, taking salt, sodium chloride, and breaking it down into its elements, sodium and chlorine. In order to do this, the sodium ions have to be reduced, and the chloride ions that are in the salt have to be oxidized. And neither of these processes are thermodynamically favorable. And this means that the overall process is not thermodynamically favorable either. In fact, the cell potential for this process is negative 4.07 volts, that negative sign indicating that it's not thermodynamically favorable. So in order to make this happen, what we're actually going to do is we're going to take our molten salt and we are going to put electrodes into it and attach a battery or other power source to the electrodes. The battery acts as an electron pump, pulling electrons from the anode and pushing them into the cathode. And if you stop and think about what needs to happen, the electrons need to be removed from the chlorine. And so that oxidation process will happen at the anode, just like it did in a voltaic process. So at the anode, the two chloride ions will lose their electrons to become chlorine gas, while as at the cathode, where reduction occurs, the sodium ions will pick up an electron to become sodium metal. Now, the voltage that's necessary to actually cause this process needs to be the opposite of the overall cell potential, so at least 4.07 volts. In practice, we often need to apply a slightly greater voltage than what would be predicted, and that additional amount is called the overvoltage. So you might be wondering why for this process we would be running electricity through molten sodium chloride. You don't see molten sodium chloride around very often. It has to get really hot in order to have melted salt. The melting point for salt is 801 degrees Celsius, so it's going to take a lot of energy to do that. Well, two reasons. First off, if you just have solid sodium chloride, you can't run electricity through it. It doesn't conduct because the ions, the sodium ions and the chloride ions, are trapped in the crystal lattice. Also, if you try to use aqueous sodium chloride, it turns out that the water is easier to oxidize and reduce than the sodium and the chlorine. So you don't get your desired products of elemental sodium and elemental chlorine. How do you decide what are the products going to be for an electrolysis process? What's going to be oxidized? What's going to be reduced? I suggest a three-step process. First thing you need to do is you need to list all the chemicals that are present in your beaker or in your electrochemical cell. So in the example I have off to the right, I'm going to apply a voltage to a beaker containing an aqueous solution of lithium bromide. So what's in there? There's going to be lithium ions, there's going to be bromide ions, and there's going to be water. It is really important that you remember to include your solvents in your list of things you have because they can do chemistry too. So once you've listed your chemical species present, you're going to look at each one and determine whether it's likely to be oxidized or reduced and what that potential associated with that process, be it oxidation or reduction, would be. In our example, the lithium ion has a positive charge. That means it's going to be easier for that lithium to gain an electron and be reduced, forming lithium, elemental lithium, than it would be to remove an additional electron. On the contrary here, bromide has a negative charge. It's going to be more achievable to remove that extra electron and oxidize the bromine, forming elemental bromine, and I am going to make a note that I will have to add 2 bromines in order to balance my equation. And so for each of these, I can look up their standard reduction potentials, or oxidation potentials in the case of bromine. Okay, so I've got those. Both of those are negative because we know this is a non-spontaneous process. Now for water, water can be both oxidized or reduced, and it's important that you recognize that water has both of those possibilities. If water is reduced, you're going to form hydrogen gas, and the reduction potential is negative 0.83 volts. When water is oxidized, you form oxygen gas, and the potential for that oxidation is negative 1.23 volts. Now, all of these numbers I pulled off a table for standard reduction potentials, making a point to flip the sign on the equations that are being oxidized, since it's the opposite of the reduction that is tabulated. Okay, so once you've noted all those reduction potentials and you know what your possibilities are, it's time to decide what's going to happen. You're going to look for the most positive of the reduction possibilities and the most positive of the oxidation possibilities, and that will be the chemical processes that occur in your electrolytic cell. Again, going back to our example, that means I have two reduction possibilities, that of lithium and that of water, and the water has a more positive potential, and so the water will be reduced. And for my oxidation potentials, I have bromide and I have water. But here the bromide is most positive, and so bromine will be oxidized. And so in my electrochemical cell, my electrolytic cell, I'll have water being reduced and bromine being oxidized. Often we want to know not only what's going to be oxidized and what's going to be reduced during electrolysis, but we also want to know how much product we're going to make. Or perhaps I want to know how long I'm going to have to carry out the electrolysis to make a particular amount of product. Okay, let's talk about the math here. So it turns out there are just two key relationships you need to have in order to do this. The first is the equation I equals Q over T. In this equation, I is the current, and this is defined as the amount of charge that flows in coulombs per unit time. And that time is in seconds, and the unit for current is the amp. So this will allow us to relate the amount of electricity in terms of the time and the current we're applying to the amount of charge that's actually going to flow through our system. The second equation that we need relates that charge, which is measured in coulombs, to something that's chemically relevant, how many moles of electrons we're pushing through the system. And this is a relationship you've actually seen before. 1 mole of electrons carries a charge of 96,485 coulombs. With those two equations, we are ready. Our general plan for this process is going to be to use the first relationship to determine the amount of charge that flows. Once we know the amount of charge that flows, we can find moles of electrons. And then we can use stoichiometry to figure out the moles or grams of product that would entail. Let's take a look at one example. If I have current pass through molten calcium chloride for 1.5 hours, how many grams of calcium metal can be produced during this process? Okay, let's start by making sure we know what's happening inside that electrolysis cell. If we have molten calcium chloride, that means I have calcium ions and I have chloride ions. The calcium ions are going to be reduced, forming calcium metal, while the chloride ions will be oxidized, forming chlorine gas. The equation we're going to focus on, because what this problem is asking about is the calcium metal, it's that first one. Okay, so we have an equation that we're ultimately going to task, but first let's figure out how much charge we're going to send through this system. We'll start with the equation I equals Q over T, but since what I want to solve for is the charge, I'll take the current and multiply it by the time. Remember that time's in seconds. You're going to have to do a little conversion here. What I find is that 2.44 times 10 to the third coulombs of charge flow. Now let's relate this to something chemically useful. Let's relate this to moles of electrons. Once we know moles of electrons, we can relate that to the moles of calcium using stoichiometry and our balanced equation. And from there we can find mass of the calcium metal that is formed. So in this process, we've gone from current and time to moles of electrons, and from there to the mass of calcium. It's worth noting, although I'm not going to work an example for it here, that you could go backwards. If you know your target amount of solid that you want or target amount of product that you want, you can work your way backwards, figure out how many moles of electrons have to be transferred, and from there either the current or the time necessary to accomplish that. So in summary, electrolysis is a process in which you take a non-thermodynamically favorable process and you make it happen by applying electricity and cause that redox process to occur. You can talk qualitatively about what's going to be oxidized and what's going to be reduced in an electrolysis cell by looking at what chemical species you have, deciding what's most likely to be oxidized and what's most likely to be reduced, and then finding the process that has the lowest oxidation or reduction potential and therefore is the most thermodynamically feasible. You can also do math. You can calculate the mass of product or work backward from a target mass of product using the definition of current, which is the coulombs per second, and the fact that for 1 mole of electrons, the charge is 96,485 coulombs.